So we're going to talk about implicit differentiation and related rates now. This video is really going to be just about implicit differentiation. There won't be any related rates in this video. But we're going to see how the stuff we did with chain rule of multiple variables can be brought to bear on problems in just the xy plane for this. So let's go ahead and look at an example. So we can have curves we're interested in, like this curve here, where we've got x cubed plus y cubed equals 6xy. And so here's a graph of this curve. And this curve can't be represented by any function of the form y equals f of x. However, we could still imagine something being traveling along a path like this. And so we might still be interested in the slope of the tangent lines, because if we have something traveling on the path, that would give us the velocity of the object. And so it's still something of interest, even if we can't write it as y is equal to f of x. So what we'd like is a method to get around this so we can still find the slopes of tangent lines of curves like this. So let's set capital F of xy to be x cubed plus y cubed minus 6xy. And we see now this is a function of two variables now, x and y. And our curve is given by when this is equal to 0. So notice I came up with this equation for f of xy just by subtracting 6xy from both sides of our equation for the curve. And now we're able to use the chain rule to get the derivative, the slope of the tangent line dx dy using the following method. So just like we had before when we were drawing our charts, we think of f and it's a function of x and y. And since there's two variables on that line, there's going to be partial derivatives. But then we also view y as a function of x. Even though overall we can't write y is equal to little f of x, locally we can do it. So we're going to think of this as a function of x as well. And now when we do our chain rule, we're going to differentiate both sides. We're going to use that diagram and differentiate both sides of this equation. So if we follow one side of the diagram, we have just delta f delta x. And then we follow the other side all the way down, we get delta f delta y times dy dx equals 0. So as long as df dy is not 0, we can solve for dy dx and just get the partial derivative, get that that's equal to negative of the partial derivative of f with respect to x over the partial derivative of f with respect to y. So you just see that equation above, subtract the delta f delta x to the other side, and then divide by the delta f delta y, and then we'll just use the easier notation here, f sub x and f sub y. So now if we consider, say, the point 3, 3, we note that if you plug 3, 3 into that equation, you do get 0, so this is a point on our curve. It's not always easy to actually find points on curves defined like this. And now if we take the partial derivatives, we have the partial derivative of f with respect to x is 3x squared minus 6y, and with respect to y, it's 3y squared minus 6x. So then we can use that to find the partial derivative, or to find the slope of the tangent line at the point 3, 3. From our formula before, it's negative f sub x of 3, 3 over f sub y of 3, 3. And if you plug 3, 3 into either of those partial derivatives, you get 9. So I get negative 9 over 9. So the slope of the tangent line at 3, 3 is negative 1. And so that tells us that the tangent line to the curve at 3, 3 is just given by y minus 3 is equal to negative x minus 3. So we see we can use our chain rule and our partial derivatives to still take a derivative of something that's just in the xy plane. There's another nice use of this method where we can use this to take derivatives of some complicated functions we couldn't otherwise differentiate. So let's just consider such a function. So let's let y be equal to x raised to the tangent of x. And so this is a mess. We have x raised to another function, so it's not so easy to see how would we actually take a derivative of this. We can't just use power rule here. So what we can do is apply the natural logarithm to both sides of this equation. And then we can use properties of logarithms to bring that tangent down to the front. So I have natural log of y is equal to tangent of x times natural log of x. And so now let's set our equation f sub xy. We'll bring that tangent of x, natural log of x, to the other side. So I have natural log of y minus tangent of x times natural log of x. So what we're really interested in here is when f of xy is equal to 0. just like before. And so we're going to use the same method. So we have f sub this partial with respect to x. We use product rule here. We get the derivative of tangent, which is minus secant squared x, times natural log of x, minus tangent times the derivative of natural log of x, which is 1 over x. And then the partial with respect to y, we just take the derivative of natural log of y, which is 1 over y. But then remember, y is equal to x raised to the tangent of x, so we can replace that to get back into just x variables. And so using the same formula we did above, that negative goes with the f sub x to change the negative secant squared to positive and the negative tangent x over x to positive. And then we're dividing by f sub y, so dividing by 1 over x tangent of x. And when we divide by a fraction, we multiply by the reciprocal. So this is our derivative of that function. So again, this was just a regular function, y equals f of x. We can see this technique of taking these partial derivatives like this can still allow us to find this derivative. And so we'll see in the regular class how we can use this to solve a bunch of problems, applied problems referred to as related rates problems as well.